All right, so finally we are out of chapter 1. Finally we can stop doing review. Finally we can get into calculus. Like we can actually talk about what calculus really is. That's what we're going to be starting into here. Okay. Now this introductory section, this section 2.1, is a very basic introductory section. It's only it's very slim on the notes. There's only 3 problems for the homework assignment. And no, it's not like A, B, C, D, E, F, G. It's not like multiple parts. But it's more theoretical, and you'll understand more why we are doing this like 2 weeks from now. You'll be like, oh, got it. That's how that worked. That's why we were doing that before. Okay. Now, again, chapter 1 was all review. Everything that we should have known coming in, that was all chapter 1. There was some stuff that we really had to brush up on, but it was more like honing our algebra skills. Now what we're going to be talking about is more what calculus really is, in my opinion. Okay, we're going to be talking about 2 different types of problems today: the tangent problem and the tangent line problem, and some velocity problems. And they go hand in hand. It might seem really weird that we're talking about tangent lines and then velocity. Those are very, very, very closely related, and you'll see why here in a second. All right, take a look here. This is called the tangent line problem. The word tangent is derived from the Latin word tangens, which means touching. If you think about a tangent line in terms of geometry, a tangent to a curve is one that will only lie right up next to it, right? It will not cross through it. It is not what you would call a secant through a circle. It is just a tangent line, one that just lies close to, one that only intersects once. And it doesn't really intersect, it just shares only one point. Thus, a tangent to a curve is a line that touches the curve just once. In other words, a tangent line should have the same direction as the curve at the point of contact. And that's going to be important here. In other words, a tangent line should have the same direction as the curve at the point of contact. Like if I draw a circle, okay, if I draw a circle and I wanted to draw a tangent to that circle, there's an infinite amount of tangents that I could draw to that circle, right? I could draw one right here. I could draw one right here. Oh, well. Yeah. I could draw one right here, right? Where all of these are only sharing one point. Well, think about what is happening at that point. Look at the curve in relation to where the line is going. If I think about going along the curve and I wanted to kind of like trace along the curve with my pen here, it actually has this, it's almost in the same direction. That's what the book says. It's in the same direction as the line, as the curve is at that point. So you have to be talking about, if you're drawing a tangent line, you have to be making note of a point, right? You have to say, okay, at this coordinate, at this location, this is where I'm going to draw my tangent line. And that tangent line has a certain direction, and it will relate to where it happens on that circle. Okay. For a circle, we could simply follow Euclid and say that the tangent line intersects the circle once and only once. Euclid, the father of geometry, the guy who made our system of geometry, he said that the tangent line to a circle is going to only ever intersect once, and that word intersect by definition means share points with. For more complicated curves, that's not going to work. Like, think about this diagram in the bottom right. Does it intersect just once? No. That's a very geometric way to say it, where it intersects only once. But it's not a more algebraic way to say it if we're looking at curves like in terms of a function. Okay. For more complicated curves, this definition is not great. Figure 1b shows 2 lines, L and T, passing through a point on a curve, right? You could think about it this way. That lies once, it crosses once, but this also crosses once. And they're really, I mean, that crosses twice, right? But I could draw an infinite number of lines going through there, right? That's only ever going to cross at that one location. So that definition's not going to be great. It's a more geometric definition, less than an algebraic definition. To be specific, let's look at the problem of trying to find a tangent line t to the parabola y is equal to x squared. Let's take a look at this. Let's explore this. Find an equation of the tangent line to the parabola y is equal to x squared at the point 1, 1. Okay, let's graphically think what's happening here. Okay, we've got our parabola, our most basic parabola that we can get, the quadratic, right? The 0, 0. Okay, we got 1, 1, 2. Make that go up a little bit more. 1, 1, 2, 4. And reflected on the other side. We don't really care about what's happening on the left side because we only care, actually I shouldn't have made that as flat as I did. We only care about what's happening at one location here. So here's our parabola. I want to find the equation of the tangent line. Find the equation of the tangent line at 1, 1. So if I were to create a line, let's put it in red here, and I wanted it to be tangent. I know I've got to pick a point, just like we talked about on the last slide. I know you always have to refer to a point where that tangent is going to be. So I've got a tangent line at 1, 1. So that's the only intersection point. Well, look at the parabola really close to 1, 1. Okay, it looks like it's got this general sloping line. So our task is to figure out what the equation of that line is. Okay, I mean, it's just a sketch, but I know that the slope is positive, right? Look at the red line. The slope is positive. The y-intercept looks like it's probably something below 0. I don't know, maybe based on it's probably not going to be 0, 0, because then it would run through the parabola, right? So it's got to be something probably below 0, 0, something down there somewhere. Probably, I don't know, maybe -1, I don't know. So what we need to do is figure out the slope. Now the nice thing is that if you have a slope and if you have a point, you can create the line, right? If you've got a slope and the point, you can create the line. I already have a point. I know I want to run it through 1, 1, right? So all I need to do, I don't need the y-intercept. Y-intercept will just come along for the ride. Oh, that's great. But what we need to calculate is the slope. That's what we need to calculate. Okay, to calculate a slope, we need y2 minus y1 over x2 minus x1, right? That's our slope formula. Okay, I know I want it to go through 1, 1, correct? If I know I want it to go through 1, 1, then I can just go ahead and replace one of these with 1, 1. Let's go. Which one did I do in my notes? I did this one. I know the slope is going to look like this: something minus 1 over something minus 1, right? Okay, now think about any coordinate that you're going to generate with this function is going to look like this. The input is x. What's the output? X squared, right? Input, output. I input x, the output is just x squared. That's the function, right? Input x, output x squared. Okay, well, what if I use that coordinate? I know it's algebraic, but what if I use that coordinate? Well, then it's going to look like this. Okay, now, that's the equation of my slope. Okay, that's the equation of my slope. Now, I know I want to calculate the slope at 1, 1, right? I want to know what the slope is going to be at 1, 1. So maybe I just plug in 1, 1. Well, what happens if you plug in 1, 1? What happens in the denominator? So I can't plug in 1 comma 1. I can't evaluate it at that point, right? So maybe I can evaluate it something really close to 1 comma 1. Well, what's the next x value that I could possibly use? If I can't use 1, that's out of the picture. Well, the next x value, maybe 2? What's 2 comma what? 2 comma what? 4, right? Okay, so what's the slope in this case? The slope would be 4 and I know that's x squared, right? 4 is x squared. So 4 minus 1 is 3. 2 minus 1 is 1. So my slope is 3 at 2 comma 4. But what did I calculate there? I calculated the slope from there to there, right? Actually, I drew that kind of poorly. I calculated the slope here to here, right? My slope that I really want is shallower, right? I calculated with 2, 4, and 1, 1. So maybe I can be a little bit more accurate. I know it's got to be less than 3, right? Shallower slope means a smaller number. Well, what if I go on the smaller end? What if I go 0? You know, I went one coordinate above. What if I go 0, 0? Right? Well, maybe that might help us understand what's going on. So what's the slope there? -1 over -1, which is 1. But again, I didn't calculate the slope at that point 1 comma 1. I calculated the point here. Sorry for all these colorful lines going on. That slope is not correct either, right? It gives me a lower boundary, right? I know that the slope of this green line is 1. I know that the slope of the purple line is 3. What do you think the slope of the red line is going to be? What can you estimate it to be? What do you think? 1.5, 2, somewhere in there? How do we make that estimation a little bit better? Well, I picked these numbers 2 and 4, right? Or sorry, 2 and 0, right? What about choosing 1.5 as my x value? Would that get me closer? What about choosing 1.4? Would that get me closer? What about choosing 1.3, 1.1, 1.01, 1.001, 1.00001? Wouldn't that keep me getting closer and closer and closer to the slope of that line? What if I thought about it from the bottom end? Okay, what if I chose, instead of 0, chose 0.5? Okay, that'd get me close, but is it still exact? No, I got to keep getting higher, right? 0.9, 0.99, 0.999, 0.9999, and that process could keep going as well. See, what we're going to be looking at here, and that's why I kind of hid these tables. Take a look at what's happening here. As I go from 2 to 1, as I keep getting closer and closer and closer to 1, what's happening to the slope? As I choose my x value to be closer and closer and closer to 1, well, watch what's happening with my slope. What's it getting closer to? 2. As I choose my x value to get closer and closer and closer to 1 from the bottom end, from the left side, what's happening to my slope? What's it getting closer to? So we can say that the slope is going to converge to be 2. You know what we're actually doing here? Did you guys learn limits in Mr. Delap's class? Did you guys learn limits? Maybe at like the end of the year. This is finding the limit. Chapter 2, the first chunk of chapter 2 is all about limits. So what am I actually finding here? I'm finding as x gets closer and closer to 1, the limit of the function goes to 2. As x gets closer and closer to 1 from the right side, and then from the left side, it also gets closer and closer to 2. And we will find, using our limit laws, that it has to match up left side, right side to be the true limit of the number. If you're going to get closer and closer to 2 on this side, you're going to get closer and closer to 2 on that side, then you can say that the full limit is 2. So we can say that the slope is 2. Yeah, we can theorize that the slope is 2. Our job in calculus is to actually figure out how to find that slope. Like, this is like the essential question of calculus. How do you find instantaneous slope? How do you find slope of a tangent line? That's what we're doing in all of calculus. Like, that's our whole first semester. We'll be doing that until Christmas. It's actually kind of fun. Not my version, everybody's version of fun. But that's just the slope. Was that what I was going for? No, I still got to do more work than just that. I found the slope to be 2, but I want to use that slope and the coordinate 1, 1 to write the equation of the line. Remember, we knew it had to go through 1, 1. We theorized that the slope, because it's converging to 2, we're just going to say it's equal to 2. And now we're going to create the equation. Y, and I like to use point slope. Y minus, I know my y. Y minus 1 is equal to mx minus 1. Again, you're going to see me use point slope more than y equals mx plus b. And then I solve for y. So y minus 1 is equal to 2x minus 2. Y is equal to 2x minus 1. So we had kind of speculated that the slope was going to be 2 and the y-intercept, it looked like it was going to be something less than 0. Turns out to be negative 1. As long as we're assuming the slope to be 2. Okay. We're going to find other ways to calculate that slope once we get into chapter 3, where derivatives come in. This is kind of the diagram showing that, picking points approaching 1, right? This is kind of showing that here, from the right side and then from the left side. Like, what was I doing here? I was looking at 1, 1, and then I'm picking a point at 2, and then I'm picking a point at 1.5, and then I'm picking a point at like 1.25, and so on. I want to choose points where Q is going to keep getting closer and closer and closer to P. And what is P? The point at which we're trying to find the tangent line. Going from the right side as well as going from the left side, right? We want that blue line, we want these two lines to match up in terms of their slope. Look at it from the left side. I'm choosing a point Q, and I want to keep getting it closer along the parabola until it almost looks exactly like P. And then we can assume that it's going to be the same slope of P. Okay, that's what we're going to be doing here. All right, so that is the tangent line problem. I am not going to do this problem if you print out the notes. I'm not going to do that problem, but what I do want to do is the velocity problem. Okay, if you watch the speedometer of a car as you travel in city traffic, you see that the speed doesn't stay the same for very long, does it? You're going fast, you're going slow, you're stopping, you're at lights, you're moving, people braking, whatever. If you watch the speedometer of a car as you travel in city traffic, you see that the speed doesn't always stay the same for very long. That is, the velocity of the car is not constant. Right? I know even if you're going on the highway, right? If you're driving on a highway, is your velocity always constant? No, you're braking, you're speeding up, you get stuck behind somebody slow, you get trapped in by a truck. You got to slow down, you got to speed up. You see a cop, you got to slow way down. We assume from watching the speedometer that the car has a definite velocity at each moment, right? You can say, okay, what's my speed? You see the cop on the side of the road, you're like, oh, how fast am I going? And you can see that instantaneous velocity, right? The speedometer is calculating the instantaneous velocity. We assume from watching the speedometer that the car has a definite velocity each moment. But how is this instantaneous velocity actually defined? Think about time. If I say right now, well, from right now to now, there's a little bit of a difference, right? Okay, so what if you try to make that difference a little bit smaller? What if you try to make that difference and leave it a little bit smaller than that? When calculating velocity by definition is change in position over time, right? change in position over time. That's what velocity is. That's what speed is, change in position over time. And how fast that rate of change increases or decreases is acceleration. Okay, let's investigate the example of a falling ball here. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. This might seem familiar to some of you guys. But now we're going to calculate the velocity of the ball after 5 seconds. We're going to calculate the velocity of the ball after 5 seconds. Okay, and I thought I had a table down there. I was just making sure. Okay, so we know that the velocity is change in distance over change in time, right? Velocity is change in distance over change in time. Now, I think we should word this. We should be a little bit particular about the wording. I don't love this. Find the velocity of the ball after 5 seconds. I wish they would have said find the velocity of the ball at 5 seconds. That's what I would hope that they would say. Find the velocity of the ball at 5 seconds. Okay, now at 5 seconds, how far has the ball? Look, I'm given 4.9 t squared, right? That's position. S of t is position. 4.9 t squared. So 4.9 t squared at 5 seconds. What's the position? Well, 4.9 times 5 squared. 122.5. Okay. So S of 5 is 122.5. Okay, that's a coordinate, right? 5 comma 122.5. All right, so what if I calculated the distance traveled across 1 second? Like from second 5 to second 6. Okay, so going from 5 to 6, the difference in time is 1, but the difference in position, okay, now I just got to calculate that, 4.9 times 6 squared. 176.4. So I'm going 122.5, so S of 6, I'll write that here, is 174, or 176.4. 176.4. So I'm going to say 122 point, going from 5 to 6, 122.5 minus 176.4. Okay, so get you a little bit. 53.9 meters per second. Now, let me ask you this: is that accurate? Accuracy is kind of a relative word here. That's over the course of 1 second. Could I get more accurate than that if I really wanted to? Yeah. What would I want to choose instead of 6? What should I choose? 5.1. What if I wanted to get more accurate than that? 5.01. 5.001. And if I continually make that number get smaller and closer and closer and closer to 5, it will converge just like the slope converged. It will converge toward the instantaneous velocity. What if I did it from the bottom end? Would it work the same way? Yeah. See, I know I'm going to get closer. If I decrease that value of 6 into 5.1, I'm going to get closer and closer to the actual velocity at that given moment, right? And so close that we can assume that the error is negligible. We can say, well, if it's close enough, then it's close enough for what we're doing for our purposes here, right? So look at the table that we have down here. You know, forgive me, I'm not going to bore you with all the calculations going through that, but look, from 5, if I were to calculate it from 5 to 5.1, 49.49. That's the average velocity from 5 to 5.1. Average velocity from 5 to 5.05, 49.245. From 5 to 5.01, from 5 to 5.001, 49.0049. Okay? And we can run those numbers the exact same we did with 5 and 6. Calculated with that 4.9 t squared. We would get 49.0049. What do you think the velocity, the instantaneous velocity is going to be? What does it look like you can assume it to be? 49? I would say the instantaneous velocity at 5 seconds is equal to 49 meters per second. And that's what you're going to be doing here. You're going to be basically running a lot of slopes. You're running a lot of slopes. And you're going to keep getting that number closer and closer and closer to the exact location that you want it to be. Why can't we run that exact location? Well, because that only gives us that 1 point, right? That's like plugging in 1, 1 when you're at 1, 1. You're not going to get a value because you're going to divide by 0. The change in, you can't make the change in time 0. I wish we could, but we're going to keep getting that change in time closer and closer and closer to 0 without ever actually making it 0. That's the idea of a limit. Okay, getting closer and closer to something without ever actually reaching it. Okay. You may have the feeling that the calculations used in solving this problem these problems are very similar to those used earlier in the section to find tangent. In fact, there is as close a connection between the tangent problem and the problem. There is a close connection between the tangent problem and the problem of finding velocities. Now, the graphs are drawn below. Okay, but what I really want to point out to you is this. Does anybody recognize what that is? Because all I did was find, that's all the only thing I'm doing there is running the calculation of the slope, right? I say, okay, I'm going to have 4.9 times, we did 5 plus 1 to get 6, right? And this is 5 plus 1 minus 5. And that's why it was the difference of 1 over 176 or whatever minus 1, whatever it was, those two values on top. Right? All we did was run those values. If I had generalized it just to say, okay, if I want to go from 5 to 5.5, well, then this would be 5 plus, the difference would be 0.5, right? The h would be 0.5. This would be 5 plus 0.5 minus 4.9 times 5 squared over 5 plus 0.5 minus 5. So the difference in time would be 0.5. What is that? Can anybody recognize what that is? We've done it a bunch already this year. That's the difference quotient. That's actually the difference quotient, which you've already done a bunch of times. So you're going to find instantaneous slope is actually using the difference quotient. Instantaneous slope, you can find instantaneous slope by using the difference quotient. And the difference quotient is basically just the value that you're looking for and then the h value. Now, what is the h value? The h value in here is how far you are away. Okay, blue please. How far you are away from the actual location that you want, right? If I wanted it 5 seconds and I choose my h to be 1, you're getting a second off from where it should be. If you choose 5 seconds and you use 0.5, you're half a second away from where you think you want to be. Just like think about it on the parabola. If I was looking at it at 1, 1 and I chose 0, well, then my difference away would be 1 value, 1 unit. My h would be 1, right? But so what am I going to be doing with h? I want to make h negligible. I want to make h as small as it could possibly be. Because if I make h as small as it could possibly be, then I'm going to be getting that instantaneous value, that instantaneous slope, that instantaneous velocity. Instantaneous slope and instantaneous velocity are basically the same thing. Okay? They're calculated the exact same way. Change in y over change in x. Change in distance over change in time. Okay? And what we want to keep doing is taking that change in distance, that change in value from the point we're looking at to the point we're trying to calculate, negligible. We're trying to make that get closer and closer and closer together until it's so close that we can say they're the same at this point. The error is negligible. Okay. All right. So basically on your homework tonight, you got 3 problems. I think it's 2 tangent line problems and 1 velocity. I think. Don't quote me on that. But you're basically going to be running values to see where it gets close to. And then you kind of can just say, well, I think it's going to get close to this. So that's where I'm going to assume the slope is going to be. the velocity seems to be converging to this. So I'm going to assume the velocity is going to be at that. That's it for section 2.1. We will start section 2.1.2.2 tomorrow, but we will not finish it. We'll continue that on Monday. Let me turn off the video.